All right. All right. Good morning. So I'll get started, and then Rick will take over midway through the presentation. So we're going to talk about data management and file systems on Expanse today. Next slide. So it's starting off with the example workflow of what typical users do, right? I mean, you log into the supercomputer, you might get your source code in your home directory. Perhaps you have a Git repository that you clone or some other versioning software that you use to kind of manage your code, and you can get that to your home directory, compile your application, and then you have a bunch of data transfers that you'll have to do, like upload your input data, possibly use a tool like Globus and move it from there to the project space or scratch space on Expanse, split the files up to fit into a local SSD if you can in your run script, and run the batch job. And once the job is done, you can either copy files back to the project space, bundle your results before you do that, and then copy those from the project space out back to your laptop or some other repository. So that's kind of a workflow of what typically might happen.
So Mahi,
yeah.
Since I redid the workflow side, I think what I want to point out to the audience is that this presentation, the idea here is there's kind of two aspects to it. One is this thing you see kind of at the beginning and end of getting things onto the system. And then there's dealing with data when it is on the system. So when Mahi shows the outline, think of this as he's going to talk about how to work effectively with the data on the storage resources on the system. And then, as you'll see in the outline, we'll get into a conversation about more dealing with getting the data on and off the system, especially your scientific input and results data.
Thanks, Rick. So going with the overview, so as Rick said, I'll basically talk about, how do you manage your data once it's on the system, how do you use it, and pros and cons of various different file systems that we have, example of a local scratch usage, talk about the Lustre file system. Specifically, I'm going to go over some of the design aspects that kind of tell you what it's good for and what it's not good for, and then kind of show what happens if you don't use it the right way. And then hand it over to Rick for the data management part, going in and out of the system. So the Globus basics, some recommendations on typically how you will use Globus, and lots of references at the end. So let me get started with the file systems aspect. So basically, why do we have them? Basically, you need a place to store data files on the system. You could have computations that have thousands of files, like that could be temporary. For example, if you're doing something, some analysis, and it's being created during the analysis, or you could need them for a longer term thing where you're checkpointing the results and keeping them for the duration of a run. That might be not a single job, but it might be a long running job that's split into several jobs, right? So you checkpoint at the end of each sub job, and then basically restart in the next job. So there's all kinds of options. So Expanse, the system itself, if you're familiar, basically has AMD ROM EPYC processors, 128 cores per node, and we have close to 100,000 now cores if you include all the racks. And we have NVIDIA V100 nodes. But on the file system side, basically we have a Lustre file system that's 12 petabytes. So one thing to know is that it is a single file system that's split into two areas, Scratch and projects, and we intend that for different kinds of use cases, and I'll talk about that. We have a Ceph file system, which is actually available now, but on a very restricted basis. and a home file system with a 1 petabyte home file system. So we basically have a tiered storage model on Expanse. So we have node local NVMe drives for workloads that basically don't need to share data files across nodes, but need a lot of temporary storage. So that's about a terabyte of NVMe on each of these Expanse nodes. And on the GPU nodes, it's 1.6 terabytes. So that's a fair bit of local NVMe that you have available. We have a Lustre file system, which is basically for IO workloads that need high bandwidth, writing in big blocks, and you need large capacity shared storage. And then we have these network file system, NFS file systems, basically, which are for your home directory storage. We also have some projects that they have their own NFS systems for project storage. But both of them are basically mounted on every node. So if you look at it, the node local NVMe is local to each compute node. So the NVMe on node 1 is not visible to the node 2 or any other node on the system, for example. The Lustre file system and the home file systems are mounted across all the nodes. Same goes for the SEP. So why do we have so many different file systems? Well, there's the performance aspect. Do you need shared access across various nodes? Is it like a short-term or a long-term thing? We have quotas on some of these file systems. If you look at performance, for example, you'll see very different levels of performance on different nodes. So if you're looking at local file systems, you might get one type of performance. And so you can see here, this is basically, I think, the NFS file system actually, this is probably the Lustre file system. That's what I'm doing here is running with like a 128K transfer size, and you can see that it doesn't do too well when the transfer size is small. But then if you do the same thing on a node local scratch, you might get a lot better performance, because that file system is better at these smaller transfer sizes. So there's that aspect of it. So the storage choices typically should be driven by the application need. I'm just taking a quick look at the chat. I think people might have answered some of the questions already. Let's see, yeah. And the capacities part I already looked at. Okay, so getting back to the talk. So basically the choices are driven by the application need. And sometimes you might have to adapt your applications as you scale. Like, for example, if you have a few small files and your job is using a few cores or a single core, writing small files to an NFS server is fine. But if you have a job that's got 1,000 cores and all of them are simultaneously writing, you'll cause a problem on the NFS file system. So there are considerations like that. So starting off with the home file system, this is basically where you land when you log into the Expanse login node. You'll be on your home directory unless you change something in your configuration, but most users don't, and you'll end up in your home directory. And this is typically meant for storing source code, some important files, maybe some small input files, but it's limited in size. So we have a storage quota of 100 gigabytes on the home directory. The thing to keep in mind is we don't have backups as such. This is more of snapshots for a few months, so 1 or 2 months typically. So, and this goes for every file system. If you have critical data on the system, don't have a single copy sitting on a live file system. Please always make an offsite copy of anything important. And that's where the tools like Globus help in moving them off and making copies elsewhere. But you definitely, if anything is critical, you should have multiple copies, especially source code and important data sets that can't be replicated or reconstituted. Please have offsite copies. So going to the next file system, this is the Lustre Scratch file system. So we are basically looking at /expanse Lustre Scratch, your username, and then the temp project. And we deliberately chose this temp_project location there so that mentally you think of it as temporary location and not a place to park data for the long term. This is typically where you would store large input data sets. It allows distributed access from all the nodes. The storage limit, we nominally actually let you go up to 10 terabytes. And if you need more than that, we can accommodate it, but we don't make it the default because people tend to park data. So we are starting out with a little lower limit, but if you do need something more, please contact us and we can raise the limit if it makes sense. The key thing to remember in this file system is that the data is purged 90 days after creation, right? So, and there is no backup, right? So please make offsite backups of anything critical. The next file system I'm going to talk about is the Lustre projects file system. It's in /expanse Lustre projects. And remember, both these locations are actually part of the same one single Lustre file system. You just have different policies of on the two different directories. Basically, the Scratch is purged every 90 days and the projects is not purged. So again, you could use it for the same kinds of data sets, input and output and large files. And also you can have some project specific data. Say, for example, you have some reference data set that is used in all your computations and you need it for the duration of your project. I would put it here. Instead of putting it in Lustre Scratch and getting it purged, you would put it in a project's location so that it's always there. You would also you can also use this location for storing your results from your simulations once you've done them. So we don't purge this location, so you can keep data here for a little longer term, basically the end of your project, which is typically 1 year duration unless you renew it. The storage limit, again, this is the total storage that we kind of normally are allocating there, but again, this is something it's an allocated space. So when you go to access to request an allocation, when you ask for Expanse project storage, this is what we mean. This is where it ends up. So the total storage limit is around 2.5 petabytes, but we typically limit projects to about 100 terabytes is where we go up to if there is justification. So this project storage will need to be justified in your access proposal or your proposal that you write for requesting time. This also does not have backups. So we don't purge it, but that doesn't mean that if there is a issue with the file system of some kind that we have a backup that we can restore. So please, again, if you have anything important, make offsite copies of the critical data. So the next thing I want to talk about is the node local storage. This is a location that you cannot see from the login node. It is local to each compute node or a GPU node. And when you run your job, the Slurm creates this, the processes that create this location that is very specific to the particular job. So the location is going to be /scratch your username, and then job underscore, and then the job ID. This location is created when the job starts, and you can use it during your job's runtime. But when your job ends, you're going to get purged in this location. So this is typically used if you have a workflow that writes a lot of small files. For example, there are some tools that write out, tens of thousands of files that they're kind of using to store integrals or something that are being reused in your computation, but they don't really need them after the computation is done. So that sort of large number of files, but small file sizes, causes problems on the Lustre file system, and I'll talk about why. And but it's perfect for this kind of non-volatile memory storage, which is basically very IOPS friendly. You can get close to, I think, 50,000 IOPS very easily from this, from each node, right? So this is all infinitely scalable because it's local to each node. So you don't really care. If you have 1,000 jobs running, each of them gets its own different NVMe there. So so you end up with basically scalability also, compared to Lustre, which is a single file system going across all the nodes. So if you run 1,000 jobs and each of them is writing 1,000 files, you're hitting Lustre with 1 million requests. So you can see how things will go out of control. So this gives you essentially fast node local access. In terms of the sizes, I think there was a question about the sizes. So that we have the compute nodes with 1 terabyte, the GPU nodes with 1.6 terabytes, and then the large shared, which is the large memory nodes, have 3.2 terabytes. Again, these are only accessible from a compute node or when your job's running, and they're purged after the job ends. So just a summary of what we looked at. So home directory purpose, you can store source trees, maybe your binary installations, important files, and so on. 100 gigabyte quota. Limited number of snapshots are available. So if you accidentally delete something and let us know real quick, we can probably recover it from the previous snapshot. But it's not a long-term backup. That is, if you had something a year ago and you deleted it a year ago and you come back a year later and say, hey, I want my file from the home directory, we won't have it. So keep that in mind. There is no Globus access to this home directory, but you can use your typical SCP sync commands or any other tool, or you can use git and SVN or any commands that you're kind of using to pull from repos. That should be fine. The Lustre Scratch is essentially for distributed access storage during a parallel job. So it's shared across multiple nodes. The user access limits, as I mentioned, we nominally say 10 terabytes, but we can change that if you have a need for it. We recognize that some jobs will create a lot of data during the runtime and probably don't need all of it at the end of it. So maybe you keep it online for a month or so. That's fine. I think we can work with you. This has Globus access, and Rick is going to talk about that. The collection to use will be the SDSC Expanse Lustre collection for that. Then the Lustre projects, again, it's a Lustre-based thing. It's again got limits which are need-based, and these limits are determined based on your allocation requests. So if you're writing a proposal, keep that in mind. So if you think that, hey, I have this input data set that's 10 terabytes that I always need, or I think I need, I'm going to generate 10 terabytes of results during my project, but I need it to be available throughout the project because I'm doing some post-processing of that during the project, then give that justification in a proposal and request Expanse project storage of 10 terabytes, and that kind of will show up. as an allocated request on the system. Again, this has a Globus access and with the same collection. Then you have the node local scratch, which is basically meant for lots of small scratch files or even larger scratch files that are generated during a job. It's purged after the job ends. And the Globus access, there is no Globus access on the compute node, so this is not going to be accessible from Globus. So the guidelines for usage, and I've talked about it, I just want to reinforce it now. So the Lustre scratch space meant for storing data for active simulation, not backed up. Do not use it as parking space for long term. There is a 90-day purge policy, and we will kind of keep running that continuously. So you will get your files purged if you leave them for the long term there. It's mainly meant for large block scalable IO, and I'll talk about this a little bit in the coming slides when I talk about Lustre itself. Then we have the node local NVMe storage, which is basically for metadata intensive jobs. That is, if you are doing lots of files, high IOPS, IO operations per second. Sometimes you have jobs that do file per core, like they write out a file for every core and they're continuously writing throughout the job. That sort of traffic is not good for Lustre, but it's perfect for this kind of storage. Key thing to remember is it gets purged at the end of the job, and I'll show you a script on how you can tar things and bring them back so that you don't lose that data if you need it. Lustre projects, again, same as the scratch space. It's meant for the large block IO, but it's again not backed up, meant for storing data that you need for the duration of a project. Home directories only for source files, libraries, binaries, and so on, but please do not use this for IO intensive jobs, because all of these shared file systems, when you do something bad on the system, it doesn't just impact your job, it impacts everybody else who's on that shared file system. So you need to keep that in mind. So a quick example of local scratch usage. So in this example, what I'm running in the shared partition with 16 tasks and kind of saying, okay, I'm showing this with a benchmark that creates data. So what I'm doing is copying this IOR benchmark executable into this local scratch and using it from there. So then I move to this local scratch location. And note that if you went to the login node and looked for this, you wouldn't find this. So this is only going to be on the node that's running your job. Then I'm just running my job. And this job actually creates a lot of data in the local scratch. And also what I'm doing is I'm redirecting it to output file, which is also in local scratch. And then at the end, I'm saying, hey, once I'm done with my job, copy this back. So this ensures that once the benchmark is done, the output gets copied out to the submit directory. So Slurm has this convenient thing that is slurm_submit_dir environment variable that basically points to the location from where you submitted the job. So if you submitted this job from a Lustre location, this copy will just copy that back there. Now, one thing to keep in mind is, say if this generated 1 million files, you don't want to be doing a copy of 1 million files back to Lustre, because that would defeat the purpose of using the local scratch. So what I would do in that case is I would just tar it straight into the Lustre location to one file in Lustre. That would basically take your 1 million small files and create maybe like a terabyte sized file in Lustre, which is perfect. So this is kind of the sample output from the run. And you can see that you get pretty decent performance from the node local NVMe here. So just some order of magnitude kind of things to keep in mind. If you have thousands of files per directory, it's good to use the node local storage. The bandwidth is in the order of a gigabyte per second, give and take a little bit. If you have tens of thousands of files, but if the file sizes, total file sizes are not that big, then you can used RAMFS if you like, or dev SHM if you want. That has helped some jobs where, like, they write, let's say, lots of 4K to 10K kind of sized files, but the total file size is still a few gigabytes. You can use memory. If you have a few hundred files that you're writing, NFS is fine. You get about 100 megabytes per second. Actually, more like 500, but roughly that's the order. And then the Lustre file system is good if you have hundreds of files, or actually more importantly, if you're writing them in big blocks. And the peak performance of this Lustre file system is well over 100 gigabytes per second. So we already went over this. So now I'm going to talk about the Lustre file system, like explain the structure a little bit. Let me see how I'm doing on time, so I give Rick enough time to finish up. So the way the Lustre file system works is there are metadata servers. On Expanse, we have four of these. And then you have clients, which are basically on your compute nodes. And the storage itself, the bulk of the storage itself is in these object storage servers. And each server will then have a lot of storage targets. So, and each storage target is actually backended by 8 or 10 hard disks. So that's kind of the structure, right? So typical Lustre file system, you have the metadata side, which keeps track of all the metadata associated with the files, and and the storage, which is a lot of drives, right? That's as I mentioned. So on Expanse, we have roughly 12 petabytes of storage. The metadata, we can store about 3 billion files, I think, and we get about 140 gigabytes per second on the file system bandwidth and 200K IOPS overall. So when you have a Lustre file system, when you do a file open from a client on a Lustre file system, it talks to the metadata server, and then once you know which OSS you're striping on, the IO goes to that OSS directly. But then there is this concept of stripe sizes. So the default stripe size on Expanse is a megabyte, and it's kind of matched with the backend on the Lustre side to get good performance. So if you have a lot of like a file that is much bigger than a megabyte, and also you're striping it across a bunch of storage targets, and you can set this, and I'll show you the command for that. Then it's going to split that file into those segments, right? So you might end up with pieces of your file on different storage targets. And remember, these storage targets could be on different servers too. So now you can see how if a file is striped and you're writing to Lustre, it's hitting a lot of different servers. It's not going to one server, right? Which means there are a lot of network operations involved, and there's latency associated with each of these network operations. It's useful because it's lets you store a large file, and when you access this file in parallel, you get the benefit of the bandwidth of all these storage targets combined, right? So there are some Lustre commands that lets you find information about the file systems. From a user perspective, the get stripe is an interesting one, the LFS get stripe. And the LFS set stripe is also useful if you want to set the stripe on a particular file or on the directory. So like if I do a get stripe on a file, it's going to tell me, oh yeah, the stripe count is 1, the stripe size is 1 megabyte, and it actually tells me which target it's landed on, right? And the stripe count and size you can get in specifically. Now, if you set the stripe to 16 and then write the file, and you'll see that stripe count is that, and then you'll get a list of targets there underneath the covers. So as I said, by default on Expanse, we set the stripe to 1. This was mainly because we realized most people don't write big files, they're writing lots of small files. So we made the stripe count as 1. So unless you're writing a huge file from parallelly from different nodes at the same time, I wouldn't set the stripe any different. But for some users, it does make sense to set the stripe. So this is an example that shows you how to set the stripe on a directory. So LFS set stripe -c the count for and the directory name. And then what happens is any file you create in the directory inherits that stripe size. So in terms of usage guidelines, some things to avoid, like ls-l, which might look nice with color and lots of things, is good. But what this does, if you say have a directory with say 10,000 files and you do an ls-l, it's going to hit the metadata server with 10,000 requests, because it's going to have all the information about that. And then it'll hit every OSS that those files are striped on to get more information. And that's going to create a really heavy dose of like requests to one server, right? And you can imagine what this will do if you have a lot of files and you're doing this simultaneously from different nodes. You could easily have 1 million requests queued up on the same node. And that could cause a problem system-wide, because now that system is responding to these requests. And if there's some other request to create a file, that gets slowed down and so on. And this is why you will see slow response on the file system if people do things like that. Also, don't do any wildcards. Like if you have a directory with 1,000 files, don't do ls*. That's going to basically do the same kind of thing. So there are options. If you do /bin/ls and then don't use these wildcard options, you can get good response. Same thing with the stripe count, right? Like if you have thousands of files, it's probably better to stick to the single stripe. But if you have a file that you write from lots of cores at the same time, you can use a stripe which is larger, so you get performance. In general, do not store like millions of files in a directory. Try to have a structure that keeps the large files in Lustre and uses the node local NVMe for really creating lots of files if you're dealing with them. In terms of what it does to the file system, the reason I want to show you what happens if you do the wrong thing is because we see this end of it, right? So if someone does something crazy on a Lustre side, you could see something like this, where this is on the y-axis, the file opens per second, and this is time on the x-axis. And you can see we are seeing about 8,000 file opens per second going on from one user. This was one user, right? So in aggregate, if everyone does this, the file system is going to grind to a halt. And what it does is essentially, because there's a limited number of amount of processing and disk access possibilities on the servers for Lustre, what will happen is it's not going to respond to all the requests, and they'll pile up. And then you see something like this, where suddenly you see a huge spike on the server side. A load average of 400 is really bad when you have only 32 cores, right? You're oversubscribing the node by 10x, which can cause system-wide issues. So this is why we kind of keep saying, think carefully what you're writing to the file system and which file system you're writing to. So at this point, I'll hand it over to Rick, and we can take questions at the end, I think.
Everyone, so my name is Rick Wagner. I work for UCSD in the research IT department, but we used to work at SDSC. I helped to build some of the HPC systems, and I worked with Mahi for many years. And this is one of those full disclosures, because I will sound like I'm doing some marketing. I used to work for Globus at UChicago for several years. And as a matter of fact, I saw that Susan Tussey, one of the outreach folks from Globus, is in the audience. So if I get anything wrong, or if you need information, we have a representative here to help out. These are random AI generated puppies. I wanted dogs chewing on data like hard drives. AI will not make puppies chew on things. I guess AI puppies are more behaved. So what I'm going to talk about in the time we have is we're going to focus primarily on using Globus, but I do want to talk about some data management concepts at a higher level, even though we're going to be very practical today. So what is data management? Think of this as, you've got files that are your input files, your parameter files, you are running an application, stuff like that. Maybe you're dealing with sensor data or something collected from a sequencer or other instrument, and you've got to move them around and make sure you have the right copy, the right version, et cetera, and then that you've got the right results with the parameters that you wanted to run on something. And then you've got it during the computation. This is what Mahidhar just helped to focus on is, okay, I've got this data set that I want to analyze, but it's in a giant tar file. And it's going to be more efficient if I unload it onto a compute node, into RAM disk, whatever I have, because of the type of operations I need to do. We inherit a lot of code from prior work as computational scientists. And, those applications may have made some assumptions about what data looks like and what good data patterns were. So that's where we end up moving data between storage resources, because that's what the code expects, and we can't spend all our time improving the code. So then we have concepts like data provenance and integrity, like where did this data set come from? Are the files the same files? If you know the concept of a checksum, we're going to talk about that a little bit, but basically making sure that as much as we trust file systems, to some extent, there's that have a second copy, maybe have a checksum or manifest or a list of the files to know that you have the pieces that you need. And if you're missing a piece, that you can go retrieve it, or you can at least identify and mark it as bad. The better you do at this, and there's some simple things that you can do, is like, how do you find the data that you need? How do you make sure that you can go back to a data set and reanalyze it? What if a colleague asks you for something? And this, I'm not talking at the high level of reuse of, how do we tie this to our publications and what level of data or analysis results should be put out as part of a publication? Like even within your own research group, how do you find a data set that another lab member is using? So think about data management as being able to help you answer some questions like, you find the files you need on the system you're on other resources. Do you know what data you have? Have you transferred or copied the files that you want to work with? And can you get to the data where you need to? Is it locked away in an archive and you've got to ask somebody else, and things like that? So one of the reasons we're going to talk about Globus today is it is a valuable tool because it provides connections between resources, particularly storage and compute resources, so that you don't have to worry as much about routine data management activities, and you can spend a bit more time on science. It's why we use tools like this to do some work that's very common and repeatable. And then you go off and think about the more specialized domain specific stuff that you are experts in. So I suspect several of you have heard about Globus. This is going to be a very short intro because I don't want to overwhelm anyone, and Mahidhar and I are planning on doing more presentations about data management and the more specialized operations of Globus. But just in a nutshell, Globus itself is a nonprofit service that is managed and run by the University of Chicago. So this means that it is basically a freemium model that is open for research and science and academic use. And that means that there's a lot, anyone can use it, but they get support from subscriptions from universities, DOE labs, some of the NIH institutes and things like that. So those of us like here at UCSD and SDSC and other major universities that use some of the premium features, as they're called, we support Globus through subscription. That way the end user is not burdened. And if you need to use Globus, You don't have to worry about whether or not your university has a subscription or if your collaborator's university has it. They will be able to use Globus and get to the data. But for those of us that do pay the subscriptions, there are additional features that we can do, we can enable for our users. It can do a ton. There's a lot of capabilities that it has in terms of data automation, building web portals, sharing data, stuff like that. But given that, I want everyone to be able to go off and have lunch, we're going to stick to the basics today and do some initial familiarity, make sure that you have the tools you need, particularly for SDSC resources, to get data from point A to point B. So the term is transfer, which basically means to copy the data between what is now referred to as a collection. There's a lot of different layers to go from different storage resources, but you will be looking at data in collections, and the primary thing you'll be doing is transferring it, which means doing a reliable copy from one collection to another. And you'll see an example of that when I give a demo. Oh, and there's a link, globus.org. So this is a slide that I got from one of the Globus team last year to give you an idea of the adoption. One of the reasons that Globus is a useful tool for our community is the level of usage throughout the international community. Many users are familiar with it. It ties into our existing identity management platforms through resources like InCommon and Internet 2. There are endpoints on most, a huge number of the R1, R2, R3 universities that most of you are from or working with, and it can talk to a lot of different storage solutions. And again, at the base level, it's still free to the end user. So anyone can get up and running with it, which means that you're not tied to like only the premium users being able to deploy it. Okay. So as I said, we're dealing with the fundamentals. And so I really want to stress something, which is that Globus fundamentally, the best thing it does, and it's been doing it for several decades, is reliably copying files from one destination to another. And so these are, the systems run endpoints and there are collections. The data moves between the endpoints. Globus does not store a copy of the data. It is not a cloud storage system, though the management layer, the part that takes the burden off of you, runs inside of a secure environment in AWS. That management layer, which is basically doing the job you would do if you were watching rsync or SCP, watches the data transfer between the two collections. If the storage goes down, it backs off and retries. If the network fails, it backs off and retries. It continues this for a period of up to about a week or longer, depending on how it's configured. And then once the data gets from point A to point B, it verifies it. It will run a checksum on it. It ensures that the data transfers via an encrypted channel if you turn on that option, which most of us do. And then it, like I said, it verifies it. And I'm not stressing here that it is large or small data. Globus has very few limits. It does cap some stuff at like 100,000 files per directory for listings and stuff like that, but it is generally very fast depending on the type of data moved and the endpoint configuration. So this is that same thing that Globus takes the burden off of you. So instead of you sitting and staring at your laptop, watching some data come off a USB drive that you're trying to transfer, you can actually transfer data off your laptop, close your laptop, take it home, reopen it, and Globus will pick up and continue the transfer. So this is the fundamental, and all of the other features either improve this or build on this. So the software that you may want to use is called Globus Connect. For most of you, if you're working in a small lab or individually on your own desktop or laptop, the type of Globus Connect, which is actually what gets attached or deployed somewhere to move the data, is Globus Connect Personal. So this is kind of like the Google Drive install or other tools where you install it under your account. It'll work behind a firewall. It'll work behind NAT, so you can take it home and it works on your Wi-Fi. I'll use it in my demonstration. And so this is what you can run in your home directory on a Linux server that you have in the lab. You can run it on your Mac laptop like I do. And it's pretty good. It is not quite as fast as Globus Connect server, but I have moved terabytes and terabytes of data through it. And it is so nice to just start it up and walk away and not worry about it. And then it tells me when it is done, or if something goes wrong, it notifies me and then I get involved. So again, I'm not watching it. For places like SDSC or what we run in our resources and at the labs and stuff, there is Globus Connect server. So if you're in a larger group or you're working with a campus HPC center, they may already have Globus Connect server deployed. So this is a server installation on Linux, and it's a multi-user environment where you can basically map access to the file systems. So that's the server process that we'll use to transfer data to and from Expanse. So the Globus Connect pieces do not provide a direct interface to the data. What we talk to is the Globus service, which fundamentally at the bottom level is a bunch of REST APIs for those of you familiar with web programming, but then it's accessible through different mechanisms. There's a Python SDK, there's a command line tool that builds on that SDK, and then there is the very convenient and well-designed web interface that I'll be showing you in a couple of minutes. So these interfaces let you scale with what you need to do. If you just want to copy a directory or copy a few files between places, things like that, the web interface is going to do it for you. 80 to 90%, probably over 90% of all Globus users just stick to the web interface. I use the CLI because I do more administration and some task automation. And then when I'm helping projects building web portals or other things, we use the REST API and the SDK. So there's a lot of horsepower there, depending on what you need. So you can get as complicated as you want, but you don't have to. All right, so I'm going to walk through the steps before the demo on how to use Globus at SDSC, and this is going to be really similar to what you'll do at other HPC or different resources. So we're going to log into Globus using our Access CI account. If we don't have a Globus account, we create a new one. If we do, we link our Access CI identity to the existing Globus account, because Globus will link different identities, say my campus UCSD one to my Access one, etc. We're going to do a search for a particular collection. This is like the SDSC HPC ones that Mahidhar mentioned. And then we're going to navigate and transfer some data. All right, let's do a demo, because nothing ever goes wrong with a demo. Okay, when you go to globus.org, you go to their homepage. There's stuff along the top that you can start reading, things like that, but we want to click the top right login button. And here is what I meant about the different organizations, et cetera. So I could go with UCSD, but because I know that I want to connect to Expanse, I'm going to look for Access, formerly known as Exceed. I'm going to click Continue, and it takes me to the Access page to log in. So Globus does not need a username and password. It uses your existing identities. There we go. I did Duo, and I come and I land on the Globus web interface, which classic file browser look will go to 2 panes. If you've used CyberDuck, if you used any other visual tool for moving data around, you're familiar with this. And here on the left are a bunch of convenient shortcuts. I'll go to my account, and as I said, these are the different identities. You might be familiar with ORCID. This is UCSD, and then here is Access. So, and there's different rules and policies that can be applied to users for those of you deploying systems, but for now, I'm logged in using my Access identity, and I'm going to go here to the file manager, and I'm going to look for collections, and I'm going to type SDSC HPC. You don't need to use the capitals, I just did. And here are the primary ones we're interested in. And if I go to Expanse Luster, what I'll see is the projects in Scratch. So one thing I want to point out, and this is repeated in the slide, is that the relative paths inside of the Globus endpoint are slightly different than what you see on the command line. So instead of seeing /Expanse Luster, you're dropped into that path Expanse Luster here. So you see projects in Scratch. Now, I could navigate down to my project, but instead, I'm going to show you another feature, which is here. You've got recents, my collections, ones that are shared with me, and bookmarks. This is my project space for one of my allocations. So SDS 190 and my old user account. And these are different folders that I have. So bookmarks make it really convenient. You can also go here and do get link if you're sharing with somebody, and it'll give you the URL. So if they're browsing the same path and you're like, oh, I dropped the data here in this folder, you should have access to it on the system. You can go here, copy the link, and send them an email. Doing a transfer is exactly as straightforward as I promised. This is my laptop, and I'm running Globus Connect Personal on it, and you can see stuff. If you're familiar with Mac, I got documents, I got apps, stuff like that. I'm going to upload an image. You go here, you select that, or you select the folder. You can set different options. I'll mention one of those before later, but these will do a lot of things that are, if you've worked with rsync, Globus has been around a long time, very familiar with rsync, you have those capabilities. But for now, I just want to transfer this one file. I'm going to click start. It submits it. And if I go to view details, or over here to the left, it'll show me the status. So this is what I mean is it's managing the data movement. I go to the event log and I see it's there. I go back to the file manager. I go here. I click the little refresh and I have a histogram. And I can actually view it through my browser because these endpoints also, oh, never mind. I should have tested that before. We'll work on that with SDSC to make sure that that level of HTTPS access is functional, but that is the basic transfer mechanism. And that's what you need to know for getting to data on Globus. Let me go back to this. Oops. Yes, thank you, Kevin. One of those things I should have known better. Okay, back to my slides and share. And we should be looking at, are we looking at this thing that says puppy and demo, or are we looking at the notes and stuff?
Demo puppy.
Perfect, thank you. All right, so to wrap up, these are actually active links in the slides that you'll be able to use when you have a copy, but now you know. You look for SDSC HPC, you have Expanse Luster, you have projects for some of the storage that's provided by other SDSC resources, and then for other UCSD users, there's TSCC Scratch, and I believe I have the base path correct. There's a lot of other collections at SDSC and UCSD, and you should search for, if you want to get data to and from your home institution or other projects, you should look to see if the data is there. And as an example, I was messing around and I typed in monkey. I'm like, how many collections are named monkey? There are a lot more collections involving monkeys, monkeypox, stuff like that than I expected. So I typed in dog. Not all of them are about dogs, but then I typed in tiger because I was trying to see if there was something from Clemson, but you get the idea. And a lot of data archives like NCAR, the National Center for Atmospheric Research, has their research data archive on there. There's genomics data sets, there's others. So where you need to get your data to and from may already be inside of Globus. All right, to get closer to the end, recommendations. Very briefly, one of the options I didn't point to at the bottom of that was recurring transfers. One of the things we like to do very often is get a copy of the data as it's being generated, or after some period of time. You can schedule a recurring transfer, say, for example, every day, to sync data from Expanse back to some other resource like in your lab. You don't want to overwhelm the file system, so I wouldn't set it to every minute, but being able to say, like, every day or every couple of weeks, take this output directory, copy it over here, and it will copy the current state of the data. So even as jobs are running, you can copy it. And then as that data is updated, it goes to the resource. We mentioned provenance and integrity and dealing with files. Lots of small files will always make life challenging. Use manifests like checksums and tools like tar and zip. I also recommend a tool called BD-BAG. This comes out of the big data initiatives from the NIH. It builds on a protocol used by the Library of Congress and others. So it's a very simple structure that includes a manifest and tools to create a zip or tar file of the data. So build some habits around that, and it helps you to define the concept of a data set. The references I want to give you: docs.globus.org. Globus support is very, very good, and they'll help you, and they've put a lot of effort into answering your questions and putting all the answers up front. So if you are learning to use Globus and you want to get started, start with the docs page. And then the only other suggestion I have is, if it's a Globus issue, like, I think something with Globus is confusing me, try Globus support. If it is tied to a particular endpoint like SDSC, email the endpoint operator to answer those questions. And with that, we are down to 1 minute. Mahi, do you want to help me here with the summary? I'll do the first bullet, you do the rest.
Sure.
So data management, organizing your data, thinking about its life cycle on and off various systems, making sure that you trust your data and where it is very critical from the very beginning to the very end in the research data life cycle.
Okay, so from going off the previous discussion we had on the file system, basically it's important to make the right IO choice, like basically which file system you choose to write to and how you write to it. And remember that poor IO choices can lead to system-wide issues that affect everybody. I think Rick talked about the data provenance aspect and data integrity aspect. There's several file system options on Expanse. We have node local NVMe for high IOPS loads. So lots of small files, scratch files, perfect for that. To the large IO, large block IO. So if you're writing in big 1 megabyte chunks, then the Lustre file system will do perfectly fine and scale. And you can get to over 100 gigabytes per second if you're really large. But typically, like even with say 8 or 16 nodes, if you stripe correctly and write files, large blocks, you can get to like 50, 60 gigabytes per second pretty easily, if it's needed, that is. But the key thing is choose the right file system depending on your IO pattern. So metadata load and performance are the considerations. The last thing I want to stress, as I said multiple times, please make offsite copies of anything critical. We've seen it way too often that people leave the only copy of their code or the only copy of their important data in Lustre Scratch, which is really, really bad, because you might get hit by the purge, or if there's a file system issue, we might lose it, and then there's no location for it. And also, like, if your allocation expires and you lose access to Expanse, then again, you're kind of losing your file that you need, right? And we've had users come back a year later and say, oh, I had my source there. Well, we can't help, right? So back up anything that is important. And actually, I would say multiple places if it's really important. Like,
yeah, I would encourage you to use a tool like GitHub for source code, parameter files, basic scripts, stuff like that. And now, given that Globus supports the automation of like, routine syncing of data through the web interface, that really helps with like identifying key directories and trying to get a copy somewhere else without you having to do a lot of work to ensure replication.
And I think that's about it. I think we are ready for any questions that come up.